Hi, hello, and welcome to today's webinar presentation. Uh, just like in every webinar that you've probably attended here lately, the housekeeping rules are the microphones for the participants is going to be muted. However, that doesn't mean you can't participate in the conversation. Use the chat feature to make any type of comment that you might have or any question. And after the presentation is over, we're going to take a time for questions and answers to do that. So let's go ahead and get started. First, I'd just like to say thank you for your time and your attention. I hope you find this information helpful for you and that you can implement it in your particular process and operation. So let's go ahead and get started. My name is David Cash. I am a member of the marketing team here, and there we go. And I've been with Mountz now for 15 years. I've been in the torque industry for over 20 years. And Mountz has been a fantastic company to work for. Mountz originally first started back in 1965 in this garage here. We then have moved to our current corporate office location in Silicon Valley. And we also were the very first company to develop the electronic torque tester. Now we do have a warehouse distribution and our Eastern Service Center located in Foley, Alabama on the Gulf Coast. And they just recently took the brunt of Hurricane Sally. However, our operations are fully functionable as they do the cleanup there. So a big shout out to our Alabama staff for helping us remain online with our orders and shipping. So let's go ahead and get into what we're going to be talking about today, along with our error proofing and how to implement that. Now, when we talk about screw counting, we are doing so with the use of an electric power tool, or it could be another type of power tool with a different type of port setup. But in this case, we're going to be looking at our clutch torque screwdrivers. We have done 3 additional error proofing webinars in previous months where we deal with our position torque control system that allows us to be able to track where the tool is in space and give the operator power only when the tool is in the right position. We've also talked about our DC tool and how we can add a count function to that, along with different types of presets and things. But today we're going to be talking about screw counting and the use of a power tool. So when we look at what are some of the risks of manufacturing, obviously we don't want to miss any type of fastener that we may be, or any fastener within the assembly process. So that particular risk is one that we want to handle, and we can do that through the use of the screw counter. If we look at other manufacturing challenges, risks that would be the torque control process. Any type of fastening that is not torqued correctly can certainly become a problem. If the particular fastener is under torqued, this can certainly lead to the fastener vibrating loose and failing. On the other hand, if a fastener is over torqued, then that can put a lot of stress on that fastener and it could put it past its yield point. The fastener then can fail, and again, we have failure within our assembly process. So making sure that we have the correct torque obviously is paramount with our particular assembly process. Now, when we're dealing with other risks that are involved, the human error obviously comes into this particular realm of when we're talking about error proofing. So any time that we can help to eliminate any type of operator influence that may be within the assembly process, if we can help guide the operator into correct functions, then that's always a good thing. And that will help us eliminate some of those human errors. With some of the other manufacturing challenges, we want to look at how we can incorporate maybe line control within the assembly process. And we can certainly track those different types of assemblies. So if we want to safeguard against our tightening failures, the way we can do that is by the implementation of error proofing processes. And again, the error proofing philosophy allows us to be able to guide the operator, help to give them feedback on if the process is being done correctly, and also gives us the ability to validate and make sure that the assembly process is done correctly. Now, with the screw counting feature, again, this works in this case with our electric tools. It gives us the ability to not only count the number of screws within an assembly process, we can have different screws within that assembly process with different drivers that can be monitored by one particular controller. And it gives us that assurance that we are doing the operation, that we're not simply just counting them to make sure that things are all there, but we are also guaranteeing that within the process, it has been done correctly in that. So the screw counting feature can also be incorporated with PLC type controls, where it can select a program to be able to be run. It can receive signals and send signals about a certain process when it has been completed and when we might be at the midpoint for some of the other PLC type of applications. So how do we do the screw counting with a power tool? So basically what we do use is the fastener as our rule for how a fastening is going to be taking place. We can use the length, we can use the thread pitch, and then we use the constant speed of the particular driver that's being used. So with those three different factors, we can help to error-proof the assembly process and to make sure that the screw counting that we are getting is done correctly and that the operation is also done correctly. So what are the different things that we can look at and what we can avoid with the screw counting process? First, if we take a look at what a typical good fastening looks like, this is the example of that. So we have the fastener run down to a certain depth at a certain speed that's being provided by the driver. Now we can measure that process in milliseconds, and allows us to be able to generate a window that is going to be acceptable for that particular rundown to be counted as a good fastening. So what are some of the things that we can detect that happen that may cause us to detect an error? So the first one is going to be a fastener that hasn't been fully seated or is not completed, sometimes called lifted screws. This certainly can happen in an area where a fastener may be recessed into an area that the operator necessarily can't visually see if the fastener has been fully seated. So in this case, the fastener, which has not been fully seated, is not going to have the same time signature as the normal operation, and we would then get what would be called a time-lapse error, meaning that the tool did not reach the full time period for that particular rundown. And we'll get into a little bit other function in regards to this fastener not being fully completed. If the operator lets go of the driver, it would detect that would also be a non-torque up type of event. But in any case, a non-completed fastener would be detected. Next is going to be if we had missing components on a particular fastener. So in this case, what makes this a little different from the previous example is that we do have a washer that is on this particular example. So if that washer isn't going to be there, that is going to have a different time signature than it would be if that washer was there. So if we're in a state where we want to make sure that the operators are applying a washer that needs to be there, or if a screw package that comes is missing a washer, that can be detected as a no good fastening and can certainly be remedied after the notification has been made to the operator. So missing components can be detected as well. And then if we have a strip screw, obviously the driver is not going to shut off. The fastener is just going to spin in the fastening thread, and that will not be counted as well. And then finally, we have what would be a cross thread type of an event. Now, the cross thread is certainly going to allow the tool to reach the torque value when it would clutch at the resistance given by the cross thread event. However, we would not, again, meet the time signature for that particular fastener. Again, it would torque way before it would be considered to be a good fastening. And then that fastener would be detected. It would not be counted. And then the operator can go ahead and reattempt to fix that fastening so we can move on to the final completion of the entire screw count. So with that system, we would then have the ability to monitor all of the fastenings and be sure that all were completed within the certain batch, and then it would allow it to restart again with the next batch assembly process, or would in turn allow for another signal to be come in to set that particular program that's going to be used. So in our case, let's go ahead and take a poll. And for the different assembly processes within your assembly, which of these types of errors do you see more frequently? Is it going to be the cross thread event? Is it going to be the strip fastener? Is it going to be the not seated or the additional fastening within your process? So we'll give you a few minutes here just to go ahead and answer that question, and then we will move on with as we look at how that process can be done with the implementation of the screw counter. All right, so within our poll, we do see that the primary result here is missing components, and followed there by some of the, pardon me, sorry, the additional responses, but the missing components there, and then fully or unfinished fasteners followed that up. So within the system that we'll be looking at here with our screw counter, it will certainly help to address all of these issues that you may see within your assembly. So the product that we're going to take a look at is the Scout 2. Now the Scout 2, again, is our screw counter. It works in conjunction with many of our electronic screwdrivers. It uses a transformer for the power supply. Now we hook the Scout to that power supply, and it allows us to be able to monitor signals from the power supply that allow us to not only track the time that the driver is working, but if we also get a torque up signal from the clutch mechanism as well. So the Scout 2 itself allows for 8 different screw profiles to be used. You can hook up 4 different torque screwdrivers to the Scout. However, each driver basically would use its own specific profile for that assembly process. So in this case, this would be done within the realms of a more cell type build. You can't necessarily hook up 4 different tools that are at 4 different stations, and you'd be monitoring different types of values. That way, this is going to be within one cell type of build. So again, 8 different profiles that we can use. We have 4 different drivers that can be connected. There's also input and output communication, again, through the use of our IOs on here that can be connected to a PLC. That would allow us to be able to have the PLC select which profile we'd like to use based off whatever signal that may be allowing for a specific assembly process to come into the station to be assembled. So that's the kind of the overview of the Scout 2. So if we want to go ahead and we'll take a look at the demo process for this. I do have the system set up for us to be able to use. And so currently we have the transformer that's being used. We have the Scout mechanism, and then we have our thread block with our different fasteners here that will run through how we program it, how it works, kind of in the overview, and show how it would demonstrate if there was an error type of an event with it. So if we take a closer look at the interface for the Scout 2, so down below here is where we have our IO connection. If we wanted to use that, there's also a USB connection that we have. The system can be programmed using a software package that is available. We also have RS-232 communication. We have our 4 different driver ports that we can use, and then we also have that connected via cable to the transformer. So within the controller itself, we can select which program we would like to use. So currently, right now, we're on program number 1. And it's showing us that we have 6 fasteners in this particular program. If we wanted to scroll up to program 2, there are 4. And we can have up to 99 fasteners in one particular profile. If that's the case, that would be used. So for program 3, we have 3. And now we're moving into areas on the particular controller that aren't programmed. And if we keep going, it's going to carousel around back to the first one, and where we can go to the down and use that function as well to get this. Now, this particular function can be disabled, so the operator can't necessarily come in and change the profile that's being used. We can also lock them out from doing a reset as well. So in this overview, we're going to leave things open so we can kind of explore what's happening with that. So if we do want to go ahead and create a particular screw profile for a specific assembly process, we can do that. So let's go ahead and do that now. So for us to be able to do that, we would need to log in to the controller. And we do that by pressing the mode button. It will then ask for our password. We would put that in, and it would then let us into the current state that I have the controller set up to right now. So this would be our parameter function. We can come in and we can change different parameters based on different needs that may be done. And then we can also go to what would be our measuring mode. So in this case, we want to first set up which profile we're going to be using. And to do that, we then need to go back into the parameter menu. And if we select the parameter here, for the first 8 parameters are going to be the number of fastenings for a specific preset, or excuse me, a specific profile. So if we're going to be using, let's say profile 8 here, we can go ahead and select that. And now we can enter in the number of fasteners that we want to go ahead and monitor. In this case, we'll use 4 as an example. And then we can select that in return. And now we can go back out to our basic operation screen here. And then we can go to what would be our measuring program here. So in this case, we are going to actually measure the fastener and how long it's going to take to run these fasteners down. And what's going to happen is the system is going to automatically create basically a min, a max, the profile that we would be using to do that. So if I go ahead and run these down, and each time that we create a fastener here, the system is going to be monitoring what that is, and it will go ahead and create that average window. So at this point, if we like the particular profile that we have seen, we can go ahead and we can assign that to a specific profile. So now we want to associate that with program number 8. And now it has been done. And we can then go back up into our mode. And now it's showing we're in program number 1. We can scroll up to program number 8. And now we have our 4 fasteners in there. So now the system is going to be looking for us to make sure that we're going to be within that torque profile and that window. And then if we run those down, so we have our no good fastening because of the over time that we have done there. So in this case, we want to make sure that the fastener is falling within that particular window. And then if we run those down again, now we have what would be our time-lapse window, or our what would be considered the under or the pre-torque value for maybe a different fastener that may have been used. We then have our good rundown for that, and it will go ahead and count that as a good fastening rundown. So if we want to see basically what would be a non-torque up type of error. If I just run the tool and we have no torque up, we see that error here. Now, if we want to measure the components, again, for this particular fastener, it would be, we have a washer that is here. So in essence, the programming for it, we should have the fastener selected with the washer, but in this case, we're running it with it, and that's going to produce our, again, our time-lapse error where it has torqued before. But if we were to reverse the situation, we would see that the washer was not there and would not be counted and allow us to be able to go ahead and redo that fastener. So if we do have a situation where we need to redo that, again, the system itself is going to allow us to reattempt those until we get a fully completed and good rundown on the screw counter. And then we would have that signal that can be sent out to a PLC or some other line control device, maybe a light tree, something like that, to add additional feedback to the operator that the particular operation has been completed. So with that again gives us kind of the broad overview of how the Scout system works, how it can detect different types of fastening errors. And so this would be basically a very low barrier entry product that would allow us to be able to help error-proof the situation and assembly that can give us immediate feedback on how the process is going. So with that, we'll go ahead and we can move into a question and answer time. And so if we have any questions or comments, I believe Chris may be cultivating those questions or curating them.
Yeah, Dave, the first question is how many screws can be counted with on a sequence?
So it can handle up to 99 fasteners for one particular program profile.
Okay. Next question was for line control, can it stop a part from moving down the assembly line if a screw isn't completed or there's another error that happens?
It certainly can. If the line control is relying on a completed signal from the Scout, then that would not allow the operation to move down the line until it does get that cycle complete signal from the Scout.
Okay. Next question was, for setting the time of a rundown, do you recommend doing some sample rundowns and then adjust the timing tolerance based off of 10 or 20 pieces rundown?
Yeah, typically the average that's going to produce for what was going to be the automatic feature would be maybe a rundown of 6. You then can go into the parameter menu and you can adjust that window accordingly to the application or to the operator, depending on how tight you might want that tolerance to be, or if you'd like to open it up a little bit as well to help combat a certain type of error that you may be seeing more of. So there, again, you can do basically as many as you'd like, but usually we recommend that you do at least 6.
All right, next question is, how many power tools can be connected to the Scout?
So virtually all of the clutch screwdrivers that we have within the Mountz product offering, so that's going to include all of our clutch tools, which would be our BF, our NF, the brushless series, our EF series, the K series. So we can go through quite a range of different tools within our catalog that can be used. Now, this system is designed to run with the STC40 but it's possible that it can be used with other systems, but there would need to be the ability to receive and send signals as it relates to how that particular tool may be functioning.
Okay. Next question. If we have more than 5 types of screws, but same torque spec, can we use 5 programs with signal inputs changing the program?
Right, that is correct. That certainly can be done. Again, those 5 different profiles would be used within the 5 different programs, and then so each one could receive a signal in, automatically change it to which profile may be best used for, or which profile is used for that particular fastening operation.
All right, next question. What is the capability for I/O communication to interface and report product level traceability?
So in this case, we can send signals that a fastening has been done correctly. We could send a midpoint count signal to the PLC if it needed some time to queue. So it knows that at a particular point, now we have so many fasteners left. To do that, we can send out a signal to say that the entire batch or cycle has been completed. We can also then receive signals in to change which program we're using based on the part that may be coming into the work area.
And then the additional question on that was, does the counter output to production tracking via some API or serial port?
Right, so it certainly can be done. We can provide the signal. At that point, that signal would have to be integrated into whatever process may be used within that particular company or assembly with that. But we certainly can provide the signal that it has been accomplished.
All right, thanks. Next question. Is the unit watching the rundown torque as well, like if there's a burr or rough threads, or just time and final torque minimum value to determine pass or fail?
So in this case, we are simply monitoring the amount of time that happens. It's not monitoring the torque because this is a clutch screwdriver. It is mechanical, and it's going to clutch out when it receives the right torque resistance for a particular rundown. So if that was the case, that you wanted to be able to collect the data for a specific torque, or to be able to maybe run through these types of burrs that may be presenting a higher torque value than the tool may be rated for. There are other ways that we can accomplish that with other types of tools, like our MDC product, or with our DC tool type of tool to be able to send and receive the actual torque values that happen. We could also maybe put a torque transducer in line with the operation to be able to send that information to a torque analyzer or another system to be able to collect that data. So again, this system is kind of the entry level into the error proofing type of operation. So we are using time with the clutch screwdriver to be able to accomplish that.
All right, thanks, Dave. Next question. When you have 4 screwdrivers connected to the Scout, what happens when all 4 screwdrivers are running simultaneously?
So the drivers can't work simultaneously. So this would be the way that this function works. It would be basically within a type of cell build where you would be using one screwdriver at one profile. You move to another screwdriver, would use another profile at a different torque value, and that input can be brought into the Scout. So we have the ability to add more than one screwdriver to the process, but that screwdriver can only be used during its part of the assembly process. So it doesn't allow us to be able to use different drivers at different locations at the same time and be able to count those. It's within the, well, basically the cell build of that assembly process that may require one or more, or 1 to 5 drivers. You can have one additional driver that can be run in through the input and output section or communication. So.
All right, thanks, Dave. It looks like that was the last question.
All right. With that, I'd like to say again, thank you very much for your interest in error proofing and helping to move your assembly to a state where your operator has less influence and you're able to track and control a lot of what's happening with your process. Again, thank you for your time. We really appreciate it, and have a good day.